In this video, we're doing MSC Nastran Optimization if we were performing a frequency response analysis. My goal in this video is to walk you through the process of imposing a design constraint on displacements for frequency response analysis. Our example for today is this very simple 1 degree of freedom system that we have here. It's a simple spring mass system we've seen in every physics and engineering textbook out there. Here on the right is my frequency response results. So here at various force and frequencies, I have the displacement plotted for me. My goal is to constrain the RSS value, or the root of sum of squares value, so that I achieve the following. I'm looking for a value of the stiffness, or K, that will yield a higher RSS value that is no more than 0.9. So here the design constraint is imposed on the RSS value, where it's not allowed to go beyond 0.9. As a result, my new frequency response result is here in blue. You can see for the most part, for the first few forcing frequencies, it's about the same as the previous design. It's not until you get to about 1.75 hertz that the new design starts having a different displacement result. So now let's go ahead and walk you through the process. Feel free to pause the video now and quickly look at this description of the model. I describe what the loading, the stiffness, and the mass value are, what forcing frequencies we are doing this for. And again, if you have any questions on how to perform an optimization of your own for frequency response problem, feel free to email me at this email address and I'd be more than glad to reach back out to you. For our optimization problem statement, feel free to view some of my previous videos. I go into more depth regarding the objective and design variable. I've already done this a dozen times, so I'll quickly glance over that and I'll put focus on the design constraint. Again, we are going to set up an RSS value for optimization, and we're going to say that this point or this value is not allowed to go beyond 0.9 meters. So now let's go ahead and walk you through the process of doing this for MSC Nastran. You'll need access to the web app. This again is available when you contact me. So here's my email address at the bottom right hand corner. We'll go ahead and click on constraints. We've already created our variables and our objectives, so we'll move on to constraints. In the analysis type, we're performing a direct frequency response analysis. So we will want to go ahead and select direct frequency response analysis on the list. And now we'll go ahead and select displacement here one time. When you click this icon one time, it creates your design constraint where we can now configure our design constraint. For displacement component, this would be the X direction. So this would be the one component, if you will, of displacement. So let me go ahead and type in a 1 there. This will be at the mass. So for grid ID, you will type in node 2. And for the upper bound, we said that the RSS value is not to go beyond 0.9 meters. So I'll type in 0.9 there. And now as for frequency value, this is where you can type in the various options available. You could type in max, you can type in min, you can type in RSS. Now let me go ahead and describe what this RSS value means actually. Here on the next slide. Here I have the description of what all these values mean. Average, for example, would be taking each point, finding the sum and dividing it by the number of points. That would give you the average. If you were to do that for this design, this would be the point in green. SSQ would be sum of squares, and that's defined by this equation here. Here in blue is what that value would be if it was evaluated for all the points. Here Orange is the RSS value for the initial design, and we are using this equation or expression to compute RSS. So each design cycle has a different value of stiffness because of the optimization process. Each difference in stiffness will create a new curve here, which will then produce a new RSS value. So now let's go ahead and go back to our web app. So we've configured our design constraint. We can now take this output, paste it back in our PDF file, and now we can go ahead and perform our optimization. And as always, I'm definitely here to help you with your optimization needs. So if there's a model you just want to go ahead and optimize and benefit from the value of this optimization capability, feel free to reach out to me at this email address and we'll definitely get back to you. Now let's go ahead and open the F06 file after the optimization. Let's go ahead and glance the bottom and make sure that there is a successful message there. Let me inspect the objective results and make sure these are the same ones I expected in my plan. Okay, perfect. So these are the same results. And now let's go ahead and discuss the results. Again, here in orange is the original frequency response curve for displacements. Here in blue is the new frequency response curve for our optimized or final design. More importantly, the RSS value. Here in orange is the original RSS value, but here in blue is the new RSS value. You can see that it's right at the point of 0.9 meters. The new spring stiffness is 1,898 newtons per meter, and the new objective or new cost of the spring is actually about 51 cents less than it once was. And so that's basically how you constrain the RSS value. Earlier in the video, I mentioned that there are other things you can constrain. You can constrain the average. So if you want to constrain the average as an example, instead of RSS here in this box, you would type in AVG. If instead of that you wanted SSQ, you would type in that. If you want the max, you would type that, or the min, you would type in that too. And these all correspond to different things as I lay out on this graph. Now, let's suppose you want to constrain every single point for each forcing frequency. Here, there's a point for forcing frequency 0, 0.25, 0.5, 0.75, and so on and so on. How do you constrain all of these points? What you can do is you can leave this box blank, and then it will constrain every single forcing frequency in your analysis. Now here's the result of that scenario. I've already taken time to take those new design constraints. And actually, let me copy these new items actually. Again, we left this box blank. We're going to take these constraints and paste them in our design model. Let me first delete the old optimization results. Let me replace the old constraint. And make sure I did this correctly. And we'll run that optimization. In this scenario, we left that box blank, which means it's going to constrain all of those individual points. As you'll find, every point is satisfied. By that I mean every point is under this red constraint, if you will. It's not until the end that's where we have the highest displacement point. And so this is where you'll reach the maximum. So this is This is where the optimization process will be limited. This point, in essence, limits the design variable k. Here, I put a constraint of 0.8, but in the example I ran right now, it landed, or rather used, a value of 0.9. So the stiffness will be, I believe, a little softer than, or a little stiffer actually. Let's go ahead and find out what we got. Go ahead and open the F06 file. And we'll see what we received. So 10, now it's 5. So this is my new design. The cost of the spring is now $5. I see that here. And now what's the new stiffness for the spring? We started with the value of 2,000 newtons per meter, and now we ended at a value of 1,000 newtons per meter. So hence, this value should be 1,000. So there you go. That's how you impose a design constraint if you're performing a frequency response analysis. In this case, we did it for displacements. In the next few videos, I explain how to do this for element force, element stress, constraint force, and the rest of my YouTube channel has dozens of other videos walking you through how to perform optimization with MSC Nastran. With that, thank you very much. And as always, if you have a question, if you want support, guidance, feel free to reach out to me at this email address. I'll definitely get back to you. Thank you for watching.